This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
The first talk is by Sofia Vallecorsa from CERN, and she will talk about quantum computing for high-energy physics, state of the art and challenges. Sofia.
Can you hear me? Yes. Okay. Cool. So this is a talk about quantum computing, but I will spend quite some time at the beginning to give you the context. Okay, I see faces of people that work at CERN, or that work with CERN. So there is a fraction of you that know very well what we do, but there is also a fraction of participants here that doesn't really know much. Besides the fact that CERN, I guess, is a very cool place. So I'm going to explain to you why CERN is actually a very, very cool place. At the moment, CERN is the world's biggest laboratory for particle physics. So what you see here is a superimpression or a design, a sketch of the LHC, the Large Hadron Collider ring, which is a 27-kilometer ring that is spanning across the French-Swiss border near Geneva. You can see the lake, you can see the size of Geneva Airport here, just to give you an idea of how big CERN is. And along this ring and along the collider, there are 4 experimental sites, 4 main detectors, ATLAS, CMS, ALICE, and LHCb. And they do different kinds of physics. But all of them are looking for understanding the basics of fundamental particles, okay? This is the place where we are able to reproduce energies that are the highest artificially, let's say, achievable at the moment. Only astrophysical objects can create particles at a higher scale than what we can do at CERN. It's also, and I typically don't show this, but I really wanted to stress that our work is based on collaboration. Okay, CERN is an international organization. 24 member states are part of CERN. It was funded after the Second World War with the idea of spreading science for peace. And so, again, you can see the numbers. I will not go through that. It's a pretty big place. We are about 3,000 employees, but 4 times as many collaborators, okay? 4 times as many. So most of the work that we do, it's actually work that CERN does in collaboration with external institutes, okay? And so this is something that you will see very well also reflected in what I will tell you today. So this is true also for quantum computing. The main or the most important facility that we have is the Large Hadron Collider. I talked about it before. What's important at this stage is what the Large Hadron Collider does. It does collide protons at 13 TeV, more soon. And it produces more, you can read it here, more than 2 billion particle collisions per second. Okay, this is a purely relativistic environment. And this sets the stage of what is the data processing challenges that we need to face at the moment, okay? 2 billion particle collisions per second means that we need to be able to process our data in real time at 40 megahertz. And if we look at detectors, the way they work, you can think of them like 3D cameras. They're actually very complex objects. Very complex cameras. CMS is not the biggest one. ATLAS, I should have put an ATLAS picture here because ATLAS is 40 meters high. It's like a cathedral, basically. They're built like billions and billions of pixel cameras. Okay, so this is the kind of data that we need to analyze. The idea is that the energy of a collision of the colliding particle is then turned into energy distributed across all of the particles that are produced by fundamental interactions, and we need to understand and try to disentangle and characterize each one of them. Okay, so another important point is what you read in the second part of the slides, and it's the fact that those detectors take about 40 million pictures per second, but most of those we throw away. Okay, we have no way of processing all of them. And I will not spend much time talking about this, but one of the fundamental aspects of all of the experimental physics at CERN is the way we do this selection. This first step, this real-time selection, is the critical step in which we decide whether the output of a collision is interesting enough to store for further processing, or we need to give it up because we just can't keep it. So once we store the particles, what do we do with them? They are stored at CERN. CERN is the main data center, which it's at the center of a much bigger infrastructure. It's called the Worldwide LHC Computing Grid, or WSCG for short. This is about 170 data centers that are spread across the world. There are different, it's actually a hierarchical structure. All of the data is stored at CERN, but then distributed across WSCG, and in each one of the further or downstream sites, there are different kind of workloads that happen. Data processing, extraction of physics features, the final analysis step where you get your physics features and you try to make your final results and understand, for example, whether an event is signal or background, but also simulation. Monte Carlo simulation is a very, very big CPU, or let's say computing resources consumption, a cause for a very big consumption. Can you actually? Oh, yes, okay. We are storing at the moment more than 1,500 petabytes of data, okay, just at CERN. Now, we do know, however, that this is not going to be sustainable over a long time scale, not so long actually, if you look at the years, the way they're mapped here. So this plot shows you how we have estimated the availability and need of our computing resources over time. And the big increase that you see, the big step that you see at around 2028, 2030 is when the next LHC run will start. Now this plot is interesting because the black lines show you what we expect, or the boundaries of what we expect we will have available, taking into account how budget for this kind of resources changes over time and how technology evolves over time, classical computing technology. And the red and the blue line are projections of what we expect experiments like Atlas in this case to need if they apply a conservative or more aggressive R&D towards all of the aspects of the data processing chain. So this means both improving computing technologies, storage, but also software and frameworks. And in particular, I can tell you that if we don't introduce artificial intelligence at a much higher level than we do today, we will not get anywhere near or the red line there that you see is actually the only one that can assure proper sustainability of high luminosity LHC computing. So this gives you an idea of the challenge. This gives you an idea of the reasons why, some of the reasons why we are looking into quantum computing, okay, as an alternative to, as one of the possibilities of solving the future high luminosity LHC and beyond computing challenges. Now, what does it mean in terms of data? I said, okay, just until now I said what we want to do, and I said what are the challenges, what does it actually mean? So when you want to study physics in a collider experiment, you need to be able to characterize the behavior of many different things. And I will get back to it. I just wanted to give you a picture of it beforehand. And this is an event display. I chose this because this is a very famous event. It's a case of a observation of a Higgs candidate. Higgs boson is a very, very famous member of the Standard Model particle group. And in this particular case, you can imagine that you might. So this is a reproduction of how the Atlas detector would see the event, with the two colliding beams that come in the center and collide here and produce a lot of particles that are reconstructed as trajectories first, as energy deposits. Those are the little yellow dots that you see, squares that you see around here. And then you will be able to reconstruct the decay products of your Higgs bosons. And in particular, those are other jets, or other quarks that are produced together with another boson. So what does it mean to try and make sense of a picture like the one that I showed you before? There are a lot of different things that we need to be able to do. We need to be able to model the physics processes, the theoretical models that actually explain what's going on, that will give us a measurement of the expectations of the expected amount and expected kind of data that we can see in our detectors. And that is also, again, it's another big or rather broad sentence that I'm using, rather general, because in fact, even at the theoretical level, there are a lot of different things that are needed. So when we need to simulate theoretical models, this means we're typically using, of course, Monte Carlo approaches. This is the standard strategy. I will not talk about classical generative AI that is being used to do or to solve similar tasks. Okay. But apart from the Monte Carlo problem itself, even just the generation of the theoretical models, of the core theoretical models, the fundamental interactions can be a problem, okay? Because if you want to describe a collision as it happens in a hadron collider, there are a lot of different steps that you need to get right. So we are typically interested in understanding phenomena out of their equilibrium state and dynamics of our processes. And this involves solving complex equations of state and understanding also phase diagrams, in particular for QCD. Those are the most complex and are the very relevant one because, again, we're talking about collider experiment. Now, what you see at the bottom is a table that will tell you or gives it's actually a rather old table. This is now quite a few years old. But it was one of the first estimates that was given to try and understand what would be like in the high luminosity LHC, so the run that will start, I'll tell you more later, that will start in just a few years, to simulate properly the large dimensionality background that we expect to have from QCD. And the result at that time, if you look at the numbers, those numbers give you like time that it would take to sample from some specific multidimensional event that we are interested in. This is measured in hours, okay? So those numbers will tell you that this will be unfeasible and unrealistic to do with classical techniques. Now, if you're looking at the experimental data processing instead, challenges are relatively different in the sense that you've seen a little bit about that when Vasilis presented yesterday, I think. There are a lot of steps that need to happen if we want to understand what was the physical process, the fundamental physical process that happened, starting from the experimental data. The data that we need to work with has a certain number of properties, and I've listed them there in the context of what we are discussing here. I think it's important to highlight three most important things. The first one is the fact that the data that we analyze, and this might be obvious, but I just want to clear the discussion here. The data that we analyze is the outcome of a measurement, so this is classical data. Not only classical data, it's actually data that is convoluted to a lot of different effects. And in particular, there is, let's say, the low energy, not so interesting physics that's describing the way particles interact with matter, which we need to take into account, which is this what happens in our detectors. There is everything that has to do with the way detectors themselves make the measurements. Okay, so those effects are something that we find in our final data, and we need to take into account if you want to get to the original, to understand the original fundamental interaction. The other point is that this data is big, really big in the sense of big data, the way this is used today. We are at the moment looking at multidimensional data sets, well, big in general numbers, but also at the level of the single sample dimensionality. Typically, you want to combine, and this is also connected to the second point, the complexity of the data. You want to combine information from different detectors that have very different aspects. And this means that you need to be able to analyze for each of the events you are interested in a lot of features. Okay, this can have or has an impact in the kind of algorithms that you can use, and this is why something like data compression is a very important step. There are other things that it's important to take into account and that might make use of quantum algorithms harder for analyzing this data, and it's the fact that, again, its size increases or will increase further with the next collider runs. But also, typically, this data can be described over a very large dynamical range. It means that there are quantities that might span over orders of magnitudes, and we need to be able, typically, of either choosing a very narrow slice of that data, focusing on that, and at that point, though, the phase space of our predictions will be very limited, or try to process it over the whole range, and that will make, obviously, a much bigger challenge at the level of the algorithms. So I'll just give you an example of what this actually means. And I chose this example because I think it's a beautiful result that the Atlas collaboration published recently. This was published on Nature. And it's at the moment the highest energy observation of entanglement in a physical system. Okay, this was a measurement that measures spin entanglement in a top anti-top quark. This was measured at the 10 TeV by the Atlas detector at the LHC. Okay, top quarks represent very interesting systems. Their most important, or one of their most important properties is the fact that they have a very heavy mass. It means that they live very little. Their lifetime is so short that they decay before anything can happen, anything else like spin depolarization, decorrelation, or hadronization process. It means that their quantum mechanical properties are passed on directly to their decay products. Therefore, we can directly measure properties like entanglement by studying the decay processes of stable particles that are produced by the decay process of the top. Okay, so this was a very, very interesting measurement, and it's actually conceptually a very simple measurement. There are a lot of, because you just measure the correlation, the angular correlation between particles, between leptons, so the analogous of electrons or muons, so heavy electrons. So you typically just measure angular correlation, and you would get a proof that whether you are observing entanglement or not. Now, there are a lot of complex details into this, everything that has to do with what I mentioned before, so this, removing detector effect. So this is actually not a simple measurement practically, but conceptually it is, because we're looking at a very clean, conceptually very clean signal. And in fact, the result of this measurement was a striking, I would say, 5 sigma evidence, so a real observation of the entanglement properties of a top TT bar sample. Now, there is another thing that it's interesting, and I think it's relevant for what I wanted to say here. And so the black is the data, the real data as measured by the detector. The red and the blue and the two limits, so anything that's beyond here shows entanglement. The red and the blue dot and the two limits are actually the theoretical predictions that we calculate using 2 different Monte Carlo models for the hadronization problem, for the Parton shower problem. And this tells you that their prediction is very different. Depending on what you choose, you're going to get a very different theoretical prediction. It's a problem that if you want to have or if you need to discover new physics. This is an area in which quantum computing could really make a difference. Okay? If you look at the details of this analysis, you will see that the uncertainty that is related to the Monte Carlo prediction, so to the way we describe Parton showers, is 10 times larger than all other experimental uncertainties. So at the moment, a measurement like this would be or could be limited by theoretical predictions. So I hope all of this will kind of show or prepare you to understand why we're looking in quantum computing. We have a lot of interesting problems where we think that quantum technologies actually, but quantum computing in particular could make a difference. So CERN launched the Quantum Technology Initiative. This was done some years ago. I'll tell you more, but let me first tell you why and how. So on the one hand, let's say that the left, well, for you is the right-hand side, sorry. The QT4F side of this picture is what I said until now. I'm trying to understand what we can do with quantum technologies for high-energy physics. It's a very important part. But there is also that side of the picture, the high energy for QT. There are a lot of technologies that we develop at CERN that could be used to advance quantum technologies. And I will not go into that detail, but there is a lot that has to do with hardware, with readouts for qubit systems, with the hardware for sensing and communication. That's why our initiative was launched with 4 main areas in mind. So there are 3 scientific areas. One is related to computing and algorithms. And you will see that we write hybrid quantum in the sense that we are interested in understanding how to use quantum computers together or in a broader classical environment. Okay? This has to do with what I said before. We have a broad classical infrastructure we rely on. What we think of as an upgrade is maybe introducing quantum computers within that infrastructure. Then there is quantum technology platforms. This is all the areas, I will not discuss it, that it's dedicated to studying sensing for next generation detectors. Then there is the part about quantum networks and communications. Not so much, we're not that interested in anything that has to do with security, but we're mostly interested in anything that has to do with distributed computing. So that is the, let's say, the approach to communication that we have at CERN. And then, of course, there is a part, I want to stress it yet again, that is related to collaboration for impact. It is a key way, a really key focus of our research. Maybe we'll skip this. I just added this slide here because you can have a look at it later on. It's on the slides, and it will tell you in slightly more details what is it that we want to do exactly in each one of the areas. Maybe one thing that it's important to stress already now is how we actually try to mix or match these different approaches. So the scientific results together with the collaboration aspect. So together with Daisy and IBM, we fostered a new community that was born a couple of years ago and was really dedicated to studying quantum computing for high energy physics. And we came up with a set of algorithms and the most relevant and most difficult or important problems, both in the theory domain and in the experimental domain. And we tried to cluster and map them to what would be typical solutions or typical algorithms that might be used to solve them. Okay, and you can see the two areas here. So from the quantum computing point of view, our research program is broad. We are interested in algorithms, applied algorithms. QML, of course, is a major topic, but anything also that goes in the direction of quantum simulations and quantum-inspired mechanisms or algorithms, it's interesting for us. We are interested in modeling algorithms and methods, so hardware, noise studies, but also the behavior, the more core behavior of QML algorithms, the same topic that has been discussed in multiple talks here, but also providing frameworks and tools. And there is a new, I mean, we don't have anything to do, I don't have anything to show to you now, but I really wanted to mention, because I'm very proud of it, that there is new work that is starting on using classical machine learning to improve readout of qubit system. I think this is very nice application. It's also because it's rooted, it's grounded on all of the work we do in optimizing readout for our detectors. So you've seen most of this already in the past days. So it's a list of all the contributions of all of the students that worked at CERN. I've presented to you in talks or posters, so I hope they received enough applause. I hope so. The other thing I want to stress, if you look at their affiliation, again, you will see that in most cases we're talking about students that come from external institutes, okay? So again, come work with us. Before concluding, I'll just give you an example. This was not presented. So I just thought I'd take some time to show you some result myself. And this is an example in which we're trying to map the use or to match the use of a tensor network to simulate some quantum states that we then analyze with the quantum machine learning algorithm. This is interesting for us from many perspectives. Apart from characterization of QML algorithm itself, it's very important also to simulate the idea of using QML on quantum states. And it's interesting also from the point of view of understanding how well we can use tensor networks to simulate a theoretical model. Okay, in this case, we use a specific Ising model. It's a honey one. Fine. The problem is the problem of reconstructing a phase diagram model. And I will skip this. People that are interested in understanding or the details of how tensor network work can go and look at how well actually this model could reproduce the behavior of the ANI model. It's relatively simple, but we could scale up to quite a few spins, 200. But for the QML study, we limited ourselves to 20 spins. This was the minimum number of spins that we had to simulate in order to have a good representation or a rich representation of the phase diagram of this model. So I don't need to explain to you what quantum convolutional neural networks are. Here, I will just give you the details of how they work for this problem. I know they're not all of a sudden the most popular models that exist. I think they work very well. I think they're very well, they're easy to understand. because they have a behavior that's very easy to map to the classical one. They might not be the best way to continue and scale to larger systems, but at the moment, we were impressed by what we could actually do with them. There are actually in this work a few interesting points to look into. So the specificity of the ANDI model is that you can totally or analytically calculate the values and the states along the axis. Okay, so you can do this also for these specific models, also for other points in the phase space. But for the sake of for the exercises, we try to understand what were the difference in performance of our QCNN in understanding the phase diagram when we would simulate the case in which we strictly restrict ourselves to the analytically calculable points, so along the lines, and whether we could actually instead train on all classes, and you can see that this actually makes a difference. The QCNN in a completely supervised environment could not reconstruct the floating phase, okay, unless we explicitly show it classes that belong to it. But what's most interesting is that if we take an unsupervised approach, then the situation changes entirely. An autoencoder was actually given a relatively large number of a relatively large system size, where the floating phase is actually evident, could reproduce it without problem. So for me, this was a very, very nice example of why unsupervised learning is much more interesting than supervised. But this is my view. So I will conclude. In fact, I need 2 more minutes. So one is to stress again that the practical approach is the focus of our research. There are a lot of interesting things that you can understand when you go beyond the theoretical characterization of your algorithms, because the devil is in the details. So this is what we focus on. We want to know what we can do with this kind of technology. So what would be the time scale for a practical application of QML in high energy physics? I'm actually not so worried about that. Because if you look at future part 1, our first big milestone is the high luminosity LHC. This is something that will come in operation in 2030 and run until the 2040s. More complex event, everything I discussed before, what we can think we can do by then. I mean, I think it's coming, what's really coming up is hybrid quantum classical computing. HPC Center has started to introduce these technologies in their portfolios. What we would like to be able to do from now until then is to prove that hybrid algorithms can have an impact, okay? And I'm interested in an impact and not an absolute advantage, but a practical advantage, something that will give me some corner or some more efficient way of processing my data. But then there is future part 2. And future part 2 is the future circular collider, which we are discussing at CERN at the moment. The feasibility study is still ongoing. We are talking about a 91-kilometer ring. You can see Geneva here, how it would look, and the Alps, and how the LHC compares to today. And in this case, well, this would be a huge collaboration, of course, but if approved, the operations wouldn't start before the 2045. I mean, and to be discussed, huh? Because this is what you're saying now, certain people don't say it. This is not recorded, right? 2045, possibly, let's be positive. And in any case, continue until the end of the century, okay? So the time scale for these are time scales for us. I am sure there is something that we will be able to do with fault-tolerant quantum computing by then. So last thing I want to say, it's a little bit of advertisement, otherwise my group at CERN will complain. Please come to CERN at the end of January. We actually moved the conference. It was supposed to be in November because we didn't want to overlap with QTML. So come to CERN at the end of January. We will talk about everything that we're doing in quantum computing and quantum technologies, so sensing and communication, for a week at CERN. Okay? Thank you.
Thank you very much. Sofia, do we have any questions? Yeah.
I hear you.
Thank you so much. That was very enlightening. Can you give us an idea what neural networks mean for, I mean, all the pipelines at CERN is a bit tricky, but So I assume there are issues with transparency and so on and so forth. Are there areas that are already revolutionized?
Transparency meaning like
with
uncertainty, So all of this is embedded. So, okay, it's a very good point. And it's a very important aspect of using in practical setting. So for me, this is something that comes by design. When you study an algorithm, you need to be able to associate an uncertainty to the response that you get. So again, we are not yet, we are not doing that systematically for all of the experiments that we're doing now, but it's something that if we want these tools to become part of the standard use, we will have to do, okay? And I don't see, so I think we can, at this stage, I think we could apply the same models or the same procedures that we use classically. I don't see a problem with that. I'm not sure if this was the, yes, okay.
Here. I have a slightly off-topic question. You talked about the entanglement in the LHC experiments, and like those entanglement tests, usually they require like you have two parties and they need to be separated in a sense. And in my head, at least, the experiments are pretty local. So I wanted to understand like what is the sense of like separation between the two parties between which the entanglement is measured in LHC experiments.
So in the entanglement experiment, what happens is that you have I think I removed it. Well, fine. So you have the two beams colliding, and then you have the two anti-top quarks that are created. They are created locally, and then they separate. And then once they separate, then you study their decay products independently, what you want to see independently, and what you want to see indeed is that you can reconstruct the entangled state or the correlated state that was originally within the anti-top systems. And you want to prove that this correlation is quantum in nature. So you can study the angular correlation. If you look at the theoretical paper, this D value is actually something that measures the trace of the correlation matrix. And so if you can set up a limit here, and if you find that your value is below that limit, then that correlation was indeed a quantum, so it was entanglement.
And if I may ask a follow-up crackpot question.
Very last.
Sorry?
Just 1 minute.
Okay, so as I understand, these quantum effects in those experiments are like happening regularly. So is there some means of exploiting this quantumness in such experiments for quantum technologies in some sense, like completely crackpot a high energy collider quantum computer?
This is the first time I hear that, I must say, thank you, because typically here it's the other way, the argument the other way around. We can have analog quantum computers, so we don't need colliders. Okay, this is so, okay, I will not comment it further. Now the problem is that, I mean, you saw the infrastructure. Probably you don't want to. It's a little bit too heavy for building a quantum computer, I would say.
Thank you very much. We need to move on, but I encourage you to be able.